Let's continue our discussion on flux balance analysis. Last time we have seen different tools, different aspects, different uses of flux balance analysis in case of industrial or biotechnology or various other field. Today we will look at some specific case studies and how FBA help these cases to achieve at a particular results. Also we will use some of the examples to showcase how these flux balance analysis are useful. So, I will begin with case study, a case study of biofuel production. So, objective is maximization of the production of biofuels from microorganism. So, let me explain how FBA helps. FBA identifies the metabolic engineering strategies to enhance the biofuel yield. Researchers can optimize different nutrient supplies and genetic modifications to boost the fuel production. This, for example, this include ethanol, biodiesel and butanol. Now, we will look at the another case study, that is the drug target identification. Now, objective would be the identification of potential drug targets in pathogenic microorganism. How does FBA help here? So, FBA predicts the essential metabolite reactions unique to particular pathogens. Now, targeting these reactions can disrupt the pathogen's metabolism without harming the host. It also accelerates the drug discovery for infectious diseases. Now, the case study 3, it is the cancer metabolism. Now, objective would be understanding the metabolic alterations in cancer cells. How does FBA help here? FBA models this cancer metabolism to identify the key differences from normal cells. It also reveals the potential therapeutic targets to disrupt the cancer specific pathways. This aids in developing a targeted cancer therapy. Now, for example, I have identified at least 20 molecules that can counter these cancer cells. Now, since I already have the entire metabolic reactions associated with cancer metabolism, I also want to see how these specific drugs would disrupt what kind of reaction, what will be the implication, and how does overall it impact the cancerous growth. In all these studies, FBA is very useful. Now, another case study is in the field of bioremediation. So, the objective would be using microorganisms to clean up the environmental pollutants. Now, how does FBA help here? FBA designs metabolic consortia to degrade a specific pollutants efficiently. It optimizes the nutrient supplies and metabolic pathways for pollutant degradation. Application, it will be in the field of oil spill cleanup and soil remediation. For example, let me describe this in bit detail here. For example, I have identified at least 10 microorganisms that can clean up these oil spills. Now, what would happen is, individually I know the performance of each microorganism in that particular environment, but what happened when all of these microorganisms work together in some consortia? We do not know that. So, FBA helps in this case. So, we have to write down the equation or the chemical reactions associated with biomass production and the splitting or utilizing of this oil spills. So, we would conglomerate all these reactions from different organisms, different uptake rate, different rate of production, different rate of synthesis, and then we can see together in the consortia how this organism will help to clean up the oil spill. Now, with this, let me change the gear and go to the different challenges and limitations in FBA. So, incomplete metabolic networks. What is the challenge here? Many metabolic networks are still incompletely characterized. So, there are some reactions which are still missing, and we don't know the exact mechanism of these complex reactions. What would happen is, all this incomplete reaction might lead to inaccurate predictions. So, what could be the solution? Continuous efforts are made to improve the network reconstruction with more accurate data. Once we have achieved all these missing pieces, it will be very easy for us to solve the problem in FBA. Another limitation is parameterization. So, FBA models are often required to estimate a lot of parameters like reaction rate, different constants, what will be the constraints or the boundary conditions, etc. And all these missing pieces, a lot of parameterization can leads to introduction of uncertainty. For example, a simple case of E. coli might require more than 5000 of reaction coefficients, or I would say the chemical reactions. So, each chemical reaction will include a lot of constraints, at the same time a lot of parameters, just like I have explained, the rate constants, etc. If the particular experimentation is not done, we don't know what will be the value of these constant or these coefficients. So, this could lead to a lot of problems. What could be the solution? So, advanced techniques like flux balance variability analysis, also abbreviated as FBA, can help account for this parameter uncertainty. Also, there are tools such as genetic algorithms and other tools which can help to predict the values of these constants. Now, another challenge is dynamic behavior. Now, imagine this, FBA assumes a steady state. So, what will happen is, in realistic scenario inside the cells, these are not always on the steady state. Cellular systems are dynamic in nature and rapidly changes over time. It rapidly changes over the availability of nutrients or availability of other competitors. So, it will be unfair in some of the systems to assume a steady state condition. So, what will be the solution? So, dynamic FBA, also abbreviated as DFBA, extends FBA to capture the transient behaviors. These are important tools that we have to keep in our head. Now, the another challenge is integration of regularity mechanism. Now, what is the challenge here? So, FBA primarily focus on the metabolic reactions and may not capture the regulatory mechanism. So, in this case, what happened is, if one particular reaction is affecting several other reactions, FBA might not be able to capture all this into a single picture. What will be the solution? There are hybrid models that can integrate FBA with other modeling approaches. They are also called as kinetic models. So, kinetic models can answer these limitations. Okay. So, we have seen all these limitations. Also, we will see some of the limitations within the FBA. So, there are some limitations such as single objective function. So, in this case, FBA typically optimizes a single objective function, which may not be a fully representation of a complex biological goal. So, we cannot optimize two or more than two objective functions simultaneously. This is indeed a big challenge in case of FBA. What will be the impact here is, multiple objective optimization approaches are needed for more comprehensive analysis, such as cancer cells analysis or complex microorganisms analysis. So another challenge is the binary outcome. So FBA often results in binary prediction such as growth or no growth conditions, which may not capture the intermediate state. So what will be the impact here is extensions like regulatory FBA or FBA addresses this limitation by considering a continuous gene expression level. Okay. So another important limitation is lack of regulatory information. FBA lacks information on the gene regulation, signaling pathway and post translational modification. So there are integrated models, example constraint based regulatory network analysis. This bridges the gap by importing the regulatory data. Another limitation is sensitivity to assumptions. FBA results can be sensitive towards the modeling assumptions such as objective functions and constraints. So sensitivity analysis help to assess if the FBA predictions are robust in nature or not. So now we will look at some of the examples where we will look very closely for FBA solutions to the given questions. Now first let me address use of FBA in environmental and in industrial biotechnology. I have considered an example just like previous one where maximization of bioproduction is required. So what will be the objective here in this case is maximization of the production of biomass in a microorganism given the conditions. I will discuss very briefly what these conditions are. So I will also provide the specific values associated with this different rate constant, so that it will be easier for students and researchers to capture a brief picture of FBA utilization in their studies. So in this case I have considered a glucose uptake rate to be 10 millimole per gram dry cell weight per hour. Units are important. You have to keep in mind that unit should be same in all these rate of reactions. Now I have also considered the biomass reactions as C10, H10, O5N. You can get these biomass reaction or the values associated with a particular organism given in terms of C, H, O and N. It is available. Now there are two biomass reaction coefficients here. One is glucose, another is oxygen. In case of glucose, it's negative of 1 of millimole per gram dry cell weight per hour, where in case of oxygen it's negative of 5 millimole per gram dry cell weight per hour. Why it's negative? It's uptake rate. So with time, if you consider the d glucose by dt, it will be decreasing over the time. That is why the coefficients are explained in negatives here. Okay. So what will be the objective function here? Let us formulate objective function in this case. Now objective function will be the maximization of biomass production. In our case we have considered this as Z. So what will be the reaction? So it will be Z equals to C10 H10 O5N, and you have to write maximize. Now you also know the coefficients values, you also know the objective function. It's time to write down the constraints. Similar to our previous discussion, let us describe what will be different constraints in this case. So first let me elaborate on the carbon constraint. It will be negative of x1 plus 10 of x2 equals to 0. For hydrogen, it's negative 2 times x1 equals to 0. For oxygen, it's negative 2 times x1 minus 5 times x2 equals to 0. Now we have nutrient uptake rates. So, we will put a constraint on the glucose uptake rate. It should be less than or equal to 10. Now, we will have to integrate all these constraints, including constraint on the carbon, hydrogen, nitrogen as well as on the nutrients. So, let us combine. So, we have to combine the objective function and constraints to a single mathematical model, and your model is ready. Now, take a time of just 10 seconds and think about how you can solve this. Yesterday we discussed about a uh, specific method to solve these problems. We know what is that. It is the linear programming method. So, here I have provided a Python code specifically designed for linear programming to solve this objective function with the help of given these constraints. So, this code will help you to analyze the different possible outcomes. So, what will be the different outcomes? What shall be the rate at which your biomass productions for this particular organism shall be maximized. What you can do is you play around with this code, take this code, change the different levels of glucose or change the different levels of available constraints, and you see immediately your values associated with these rates for the maximize biomass production will be changed. Okay. So, with this is one example, we will be looking at several of these examples and let you know how these are useful in industrial biotechnology or in any case particularly. My second example will be the maximizing the ethanol production in yeast. It is one of the very oldest method, the ethanol production using yeast. Now, we have arrived at such conditions where we need the maximum productivity associated with yeast for ethanol production. So, there are a lot of approaches, scientists have been doing this for centuries, but we will see how FBA helps us to get those exact rate constants. In this case, let me tell you the different reactions associated with it. So, first one is glucose uptake rate, again it is 10 millimole per gram dry cell weight per hour. Ethanol production reaction is C2H5OH. So, what will be the objective function? It is a maximization of ethanol production, that is C2H5OH. Now, what are the reaction coefficients? It is glucose, it is negative of 1 millimole per gram dry cell weight per hour. For ethanol production, it is 1 millimole per gram dry cell weight per hour. You see, ethanol is rate of production, that is why it is positive in nature. So, now let us define what will be the objective function in our case. Now, let me define what will be the objective function in our case. So, for objective function, the objective function equation will be maximization of C2H5OH. Now, let us focus on the different constraints. First constraint will be on the carbon. It is negative times 1 times x1 plus x2 equals to 0. It's for hydrogen it will be negative 2 times x1 minus 2 times x2 equals to 0, and for oxygen it is negative of x1 equals to 0. Now, so let me also write the constraint for the glucose uptake rate. It shall not increase the, it should be it should be less than or equal to 10 millimole per gram dry cell weight per hour. Now, we have to combine the all these objective function as well as we have to combine the constraints, and we have to formulate a particular mathematical model and give it to some programming. So, some of you might be thinking why we are using Python in our case. Remember that when I was discussing the tools, we had a lot of option. So, you can use MATLAB, you can use other tools to solve this. So we have used Python in this case because it's freely available and it's easy also at the same time. You can use a lot of technique. In during when I was studying all this, I worked on MATLAB. I find MATLAB very easy um, because I am biased and I started learning all these methods with MATLAB. That's why I find it relatively easy. You guys can choose different languages what you prefer. So in the description I will also provide these codes associated with this. Just play around with different data and see how different constraint or different constant rates can affect the rate of production of ethanol in case of yeast. And you can also integrate the same problem with other organism. So if you have might have noticed, for the entire rate of equations, yeast parameter or the parameter associated with organism is not pictured here. That is what we were discussing in when we were discussing the limitations associated with it. So when you have the entire metabolome of a particular organism, where the biomass production or the ethanol production is just not rely on just 2 to 3 reaction, these are challenging cases, and the actual is also represent the actual scenario. For example, in the previous example, if you see the complete metabolome of yeast, it will require just a made up number. You can cross reference it with the actual Keck database, but it should be at least more than 3000 reactions. So you have to incorporate all those reactions and you have to provide a particular constant associated with each of these parameter, and your program could solve all this problem. So that is why in the start of these lectures we studied the different concepts of vector algebra, matrices, etc. And in between also we had some brief lectures related to coding methods that will be used for this particular course. Not only for this particular course, but you can utilize it for different other purposes. That is why we have structured this course accordingly. So use of mathematics, use of coding, and now use of computational approach. So you might be thinking, so when it comes to a lot of reactions such as 3000 or 4000 reaction, what will be the strategy? So in the matrix algebra you might have studied how matrices will be used to solve the linear system of equation or linear system of ordinary differential equation. And during the coding program you might have seen how you can use codes to solve the problems of matrices or the problems in case of ordinary differential equations. In case of MATLAB, you might have seen the ODE 45 or ODE 23 solvers. They can solve a system of linear equations similar to the above problem. If you have encountered 3000, 4000 reactions, you can replace these number of reactions with the help of matrix algebra. So what you will be left with? You will be left with a matrix that will be containing all these different coefficients values or rate values, and that is called as stoichiometry matrix. And there will be a column matrix that will be associated with what these constants are associated with. For example, in previous case it was minus 2 times x1 plus 2 plus x2 2 times x2 equals to 0. So in a single matrix the minus 2 and plus 2 will be abbreviated as the stoichiometry matrix, and in a column matrix the x1 and x2s are your variables. It should be equated with what you have on the other side of equals to. So what will be the values or different constants associated with these production or these rates. So with the help of matrix algebra and the linear programming, you will be able to solve these complex problems within a fraction of seconds. Okay. So, let us move to third example. I have considered the example number 3 as determining the maximum oxygen uptake rate. Now, you might have observed I am not including any organism or something like that. So, it is regardless of which organism or which particular purposes you will be using it. Your objective is to determine the maximum oxygen uptake rate, also abbreviated as OUR in a setup. So, let us see what are different reactions. So, different reactions. So, the oxygen uptake rate will be the X1, that will be millimole per gram dry cell weight per hour. Okay. So, let us formulate the objective function now. Z equals to X1, maximization of this X1. So, in this case what will be the different constraints. So, let us describe this constraint as first, it will be mass balance constraint. What will be the mass balance constraint is carbon constraint. So, carbon constraint will be minus of x1 equals to 0, hydrogen constraints will be minus of 2 times x1 equals to 0, oxygen will be minus of 2 times x1 will be 0. So, now let us integrate these two objective function as well as constraint and give this equation to our code, that is in case of linear programming. So, first in the linear programming you will just first explain your objective function and then explain different constraint, and you give these two to a linear programming coding solution. It will give you the maximum oxygen uptake rate. And why it is only limited to the oxygen uptake rate? You can give the same code and same information to other constraints just like nitrogen uptake rate. So, nitrogen uptake rate, it is very essential in some of the very industrially viable components or where these components will be synthesized. For example, the synthesis of different fertilizers, what you will be left with is you need to sparge these gases in case of nitrogen or ammonia or any source which can provide nitrogen to a system. Now, let me briefly discuss this. I think it will be foreshadowing if I do not explain all this. So, in laboratory setup, what you will be having is you have a chamber, a closed compact chamber called as fermentation unit. In this fermentation unit, you will be given as a media that will contain different growth components such as the carbon source, nitrogen source, oxygen source, etc. And at the same time you will inoculate a very small fraction of microorganism to it. So, what will happen is with the time the biomass will increase. How biomass will increase is these microorganism will divide continuously and give rise to higher biomass, and if they utilize oxygen or nitrogen or ammonia or any other gas, you need to sparge these gases. So, all these components are essential. What are these components? If you have provided glucose, what shall be the glucose uptake rate? If you have provided nitrogen source like peptone, beef extract, etc., what shall be the rate of utilization of these different components? What will be the oxygen uptake rate? What will be, if other components are required, what will be the, and how all these components acts together and it will be used by microorganism to increase the biomass rate. How you can calculate is using FBA. You can exactly predict what will be the maximum biomass production rate at the given rate of the given rate constant of these different parameters. Okay. So, let us use just one more example and then we can summarize today's lecture. So, next example is the minimizing carbon dioxide emission. So, it is very essential to minimize the carbon dioxide production in a microbial process. So, in some cases, so the given reaction will be the CO2 production rate, that's, let us assume it's x1 millimole per gram dry solvate per hour. You will also have to formulate the objective function, that is maximization of x1, and you need to formulate the constraints, and it in this case previous similar to the previous one, the carbon, hydrogen and oxygen, and the nutrient uptake rate if it is applicable in your case. But we all knows that under the microbial setup we all utilize glucose most of the time. So, you can also integrate the glucose uptake rate constraint, it shall not increase more than x millimole per gram dry solvate. So, you can integrate all these, and again you can give to the linear programming coding solution, where it will solve your objective function for given constraint and tells you exactly what shall be the values of these different constants to maximize or to minimize in this case. Okay, now I remember. So, this is the only problem where we have utilized, where we have used the minimization aspect. What will happen is, most of the time we use minimization or maximization function. So, for maximization the objective function becomes negative. It is one of the very standard method that is used in case of optimization problem. Okay. So, I hope these solutions will help your studies to find a new direction. I will strongly encourage the researchers to go through these programming methods and go through different examples and take bigger set of these problems and solve it for your given case, if you are using the microbial microbes or the cancer cells or etc. Not only this, you can also utilize these methods in case of population dynamics or population genetics. What happens is, you have a limited resource. For example, grains are available as 500 metric ton for given population, and there are different 5 set of organisms that are dependent on these grains. So, you can formulate the equations and you can formulate the what shall be the rate constant associated with this to maximize the number of organisms in each category, or if you have to maximize a one particular category, what shall be the different rate constants. Okay. So, with this let us wind up today's topic. We will meet again in the next topic. Thank you very much.